Start the recording. Okay, today what we're gonna do is we're gonna talk about continuity. Also, yeah, if you guys have any questions, feel free to let me know. Let me know, especially if the the quality is okay. I think I got most of the problems out, so it should be fine. But basically, we're going to talk about continuity today. Now, continuity basically says whether a function is continuous or not, and it's kind of like expanding upon limits and whatnot. So there's a definition of continuity, and the way we test continuity here is with these three criteria. So basically, continuity says this: a function f of x is continuous at c given that f of c exists, limit of f of c, or limit as x approaches c of f of x exists, and whoops, this is what happens when you try to rush your PowerPoint, equals f of c. 1 and 2 are the same. Okay, I'll explain what this means in just a second. But yeah, basically it says these three things. These are your three criteria for being continuous. If any one of these fail, then you cannot say that your function is continuous. This is the algebraic version. I'll be showing you guys the geometric version in just a minute. But this is basically the idea of something being continuous. And again, continuous, we're going to talk about what it is, but this is the three criteria for now. Number one, f of c must exist. F of x, limit as x approaches c of f of x must exist, and 1 and 2 must be the same. So basically what this is saying is something like this. If I take f of 3, and this is equal to 7, my limit as x approaches 3 of f of x should also be equal to 7. And it should exist to begin with. So for example, if I were to show you something a little bit more graphically, I have something later on, but basically this is the Morimoto definition. When you're looking at this in terms of geometry, basically the idea is you're able to draw the graph without there being any holes, without there being any jumps, and it's just, you can draw it without lifting your pen or pencil or writing instrument off of the paper. So for example, if I were to draw something like this is a continuous function. If I were to draw something like this is not a continuous function because I had to remove my pen from my paper. That's the general idea behind continuity. Continuity is used later on when we're talking about things like derivability and when we're talking about how we're able to do certain things with certain functions. But basically, the main takeaway is, for now, we just want you to know how you can tell something's continuous or not. So later on, once we get into how we use it, we say, okay, did we run through our checklist? Did we make sure that this was continuous before we applied these theorems or before we applied these techniques? Okay. So again, this is the basic way that we're looking at continuous when it comes to graphing. Now, when we're looking at it algebraically, the Mori definition is saying, hey, your expectations, what your limit is. Remember, limit is saying what happens when it approaches, what happens when it approaches. Hey, look, it's both going towards the same number. We have an expectation. And the reality is, hey, if you look at that number, it's actually going to be there. Remember when we talked about limits, we said we don't care where the actual number is because the limit's just saying what happens when we get really, 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 really close. That's what's different in continuity. Continuity says, all right, that actual number has to be there too. Now, it doesn't need to be a smooth graph like this. It could be something that looks more like this. Or it could be something that looks a little bit more like this. Or like this, and then like this. It doesn't matter. As long as you don't lift your pencil up, you can say that it's continuous. Now, one thing that you have to know, though, is when we're talking about continuity, we often talk about continuity on intervals. Is the PowerPoint on Google Classroom? I don't think I put it up. Thank you for reminding me. But basically, when you're looking at continuity on intervals, what you're really looking at is you're saying, hey, is this continuous on this interval? So if I have something that looks like this, this is something called a step function or a greatest integral function. But something like this obviously isn't continuous. But if I say, is it continuous on this interval right here? The answer is yes, it is continuous on that interval. Again, the main idea behind continuity, if you're looking at it graphically, is you're just saying, can I draw it without lifting my pencil? Okay, so I'm adding a classwork assignment right now. I don't have your homework because I have to adjust it and I need to fix it just a little bit, but I'll just throw up the PowerPoint on there for now, and then I'll upload the assignment right after. Again, sorry for the sloppiness today. There was just like I had a couple meetings this morning, and then this other meeting came up, so a little bit behind. Okay, it should be assigned on Google Classroom now. Thank you for reminding me, Rocky. Okay, any questions on the general concept behind continuity? Okay. If you have questions, feel free to type them in. If not, I'm going to go forward just a little bit. Now, as I give you this over here, do you guys all know how to read this? Like, on a scale of 0 to 10, how like clear is this? Like 10 being I know some of those things, 1 being I have no idea what's going on, 0 being like, oh my gosh, this is like, what is this even? If I wrote this, do you guys know what this means? Okay. There's a couple of different things that you guys need to know. Then there are two major symbols here. Number one, this like single-sided absolute value, this vertical line, this means such that. And basically when you're saying such that is you're saying you're defining C for something. Like you're saying, okay, C is defined as an even number. So if you wanted to say C is an even number, you could say something like C such that C is even. This is poor mathematical writing, but basically that's kind of how you're using it. That one-sided absolute value is such that. This here means exists in or on. So what you're saying here is I'm choosing a C such that C exists on the closed interval 1 to 5. Basically, all of this is saying C is less than or equal to, or is greater than or equal to 1, which is less than or equal to 5. That's what this is saying. This is the way that they'll generally write it in calculus textbooks. A lot of times when you define variables and whatnot, this is kind of how you're going to do it. You're going to say, I'm choosing a variable C such that C is this, or such that C is a function of this, or such that C exists on the natural numbers or all real numbers, right? That's kind of how you're going to be writing it out. Again, this isn't something that popped up a lot, but this is pretty standard writing when you're using when you're taking like AP Calc exams and stuff. So if I ever throw out something like this and you don't know what it means, make sure you stop me because I'm not sure what you know and what you don't know. In my mind, I'm assuming you don't know any of these symbols, so I'm going to be teaching you as we go. But if you ever forget, no worries. Feel free to let me know. But again, this is basically saying C exists in, or C can be defined as, or C is found in this set or something like that, or on this interval. That's what this backwards E symbol looks like. Okay, doing all right? So again, this is just a way of saying C is between 1 and 5. Now, so what we're saying here is f of x continuous, assuming f of x is x squared plus 6, is it continuous for all C's on the interval 1 to 5? So the first question is there any C that you can choose here that would break f of x? So that's the first thing you always check for. Any C's, any x values. That's the first thing you always check for. Are there any illegal x values? Because remember, the first criteria is that f of x exists. So yeah, there's no illegal x values here because there's no way that you can make your denominator 0. You're not square rooting a negative number, so you're totally fine. All of your f of x's exist. Secondly, is you're saying, are there any like weird jumps or anything? And the way you check this is normally with, is there any piecewise? If there's no piecewise, then generally you don't need to worry about these like jumps or these random, okay, I'm going here and then I switch it up and stuff like that. And if these two work, then generally your third one is okay. For these really basic functions. You're almost never given these basic functions, but this is kind of the checklist we're running through in our head. So is it continuous? And if you're ever not sure, you can just check the graph. And the way we graph it, as you guys should all know by now, is 1, 2, 3, 4, 5, 6. and then this little happy face like that. And we're saying from 1 to 5, are there any jumps on this interval from 1 to 5? The answer is no. So then we can say, yes, it's continuous. Do we sort of kind of get the graphic interpretation for now? The graphic interpretation. The algebraic, I'm assuming will make more sense once I start breaking it. But do we get the graphic? All right, looks good, looks good. What do I mean by jumps? So what I mean by jumps is we're saying something like, oh, we're starting here, but then all of a sudden it switches up to this, kind of like when I was talking about that step function. Okay, moving on. So for here, is this continuous for all C's such that C exists on 1 through 5? So same idea. So the first thing that we have to check for is, does f of x exist for all of these? And the second I see a square root, in the back of my mind, I'm thinking, okay, I know that square root can't be negative, so let's find out where this is equal to 0. So 3x minus 5 equals 0. So that means we know x has to be equal to 5 over 3. That's where it's equal to 0. So that means for this to be true, we know that x has to be greater than or equal to 0. So that means x is greater than or equal to 5 over 3, excuse me. 1 is smaller than 5 over 3. That means we cross the line into the negatives. So that means, is it continuous? The answer is just straight up no, because it breaks rule 1. Rule 1 is that for all of these xc's over here, I can plug in any c and I'll get an answer. I'll get an f of x. But I can't. I break it. Does this make sense why I break it? We're doing okay. Good. You don't even need to check the others, honestly, at that point. Now from here, we're at a piecewise. So off the top of my head, first thing I look for is, number 1, are there any illegal x's? Now I see this over here, and in my mind I'm thinking x can't be negative, but according to this, we're only using this part of the piecewise where x is greater than 0. So do I have any c's where I'm not allowed to use here? Or do I have any c's where I break f of x? The answer is no, so this one's good. Secondly, does the limit exist? And as we talked about last time, the way that you can tell the limit exists is if on the left side and the right side, they're both going towards the same number. So we're going to check this side over here, my left side. We're going to check my right side here and make sure they're both going to the same number. So let's check it out. Limit as x approaches 0 of x squared minus 3 should be the same, or from the left, I guess, as the limit as x approaches 0 from the right of 3 square root x minus 5. So we're testing to see if the limit exists, right? Those were our 3 criteria. I'm just going to refer back to it one more time. Number 1, f of c has to exist for all the c's. Next, we're checking to see if the limit exists. And the one area where the limit wouldn't exist is right at that piecewise, the bridge between the two piecewise. The left side and the right side might not match up. So let's test it. So let's plug it in. When we plug in the left side, we're left with 0 minus 3. So we are left with negative 3 equals 3 times 0, which is 0 minus 5, negative 5. Negative 3 is not equal to negative 5. So because they're approaching different things, the limit does not exist. And because the limit does not exist, it breaks rule 2. And since it breaks rule 2, what we're going to say is that it's not continuous. Do piecewise always have a jump? Not necessarily, because some piecewise look like this, where here, let me just give you a really quick example. Oof, sorry, this is rough drawing. So this here is a piecewise. And this piecewise here is the piecewise f of x equals negative x. Sorry, let me need more space. Where x is less than 0 and x squared where x is greater than or equal to 0. there's no jump here, right? It just changes the shape. So originally I'm at a linear, but once I hit 0, it switches to a parabola, which is how I kind of get this over here. And then that's what this is saying here. There's no jump, but that's why we always check it for a jump. And then that's why we're doing our little limit thing over here. We're checking to see if there's a jump. Okay, does this make sense how we're checking to see whether something is continuous or not? Algebraically now. Okay, so again, perfect. Anton asked a good question. He said, can I repeat how I confirmed step 1? So I'm just going to recap what I'm running through geometrically first. So geometrically is easy. Graph it out and then just look at it. If there's any jumps, you don't need to worry about it. But algebraically, what you're going to be doing is number 1, to check number 1, all you do is you say, are there any x's that make my function illegal? And so the two things you're looking for is negatives inside of your square root and zeros in your denominator. So it's kind of similar to like your horizontal asymptotes kind of stuff. Does that make sense? Like the general idea for checking number 1. We're just looking for illegal x values. Okay, now the way I was able to confirm it specifically for this case over here is I said, wait a minute, I see a square root here. We got to be careful. I can't have any negative x's inside my square root. So even though the interval says I use -1, I'm not using this function for negative x values because specifically according to the boundary labeled in the piecewise, we're not going to be using it. So we're saying, oh, okay, I'm not using this for any negatives. I'm not breaking any rules, not breaking any rules on the top. So we're totally fine. Does that make sense how we specifically check it for this one? Okay, cool. Any questions on this? Now that's how you check the first two. Now the last one is really similar. Basically what you're going to do then is if 1 and 2 check out, all you're going to do is you're going to just make sure that the third one says 1 and 2 are the same. So let's say, just for the sake of argument, that on step 1 you got -3 equals -3. So that checked out. Number 1 was checked out. So you're like, okay, if I plug it in, I'll get an answer for everyone there. And then number 2, you're saying the limit is equal to, as x approaches 0, equals -3. Again, just for the sake of argument, it wasn't this case. And then this third one, all you're going to do is say, okay, what happens if I plug in f of 0? So it exists everywhere, but what is it for f of 0? F of 0 is going to be 5. F of 0 equals 5. Limit as x approaches 0 equals -3. Wait a minute, one's 5, one's 3, so no, it breaks this one. Because again, what we're saying here graphically is we're saying, okay, hey, look, from the left and the right, we're both approaching -3. But at -3, it's actually, or at 0, it's actually 5. So you have this kind of like dot that's floating up in space, which we showed you a couple of examples previously. This here breaks continuity because again, I can't draw it in one straight line, and the way we see it algebraically is my limit doesn't match up to what we got. Our expectations don't match up to our reality. Again, sorry I'm kind of going over this a little more vaguely. It's just because, again, I'm trying to condense this a lot. So I'm saying, okay, we're just going to kind of hand wave a little bit, give you general ideas, and then let you kind of work it out on your homework, which I will be posting this afternoon. Questions? Okay, I'm not seeing any questions, so I'm going to be moving on. If you have questions, again, feel free to ask. So there are a couple of different discontinuities. There are 4 discontinuities: removable, jump, infinite, and oscillating. I'm going to zip through it. I'm going to show you an example of each. So number 1 is removable discontinuities. It's basically when f of x does not equal the limit. So this is the one where we say 1 and 2 both work out. F of x exists, or f of c exists. Limit as x approaches c of f of x exists, but they're just not the same. So if I have something like this, we're saying, hey, look, it's totally fine. They're both approaching 1, but at x equals 1, it's actually 0. So when you have this little dot that just like falls out or it's removed, that's a removable discontinuity. Next, we have jump discontinuity, and that's where you have your piecewise and your limit doesn't exist because it starts going towards 1 over here, but once it gets, or maybe half, but actually at 1, it's like 1.5. It jumps, like the graph switches up and then they just don't connect at all. Left side and right side don't connect. That's a jump discontinuity. And we've already been saying, hey, it jumps. Like the whole thing just jumps. It's not a single point that moves, the whole thing just jumps. Infinite discontinuities. Now, if you look over here, technically, the limit as it approaches is both infinity and stuff. But the thing is, you can't draw it with one singular line. They never actually meet up. Yeah, they're both going to infinity, but they never actually meet up. It doesn't need to be like this, though. Infinite discontinuities are wherever one side goes to infinity. So whenever you have a vertical asymptote, and you have some sort of like something goes to infinity or negative infinity, that's an infinite discontinuity right away. And it breaks continuity because number one, it breaks number one. This f of a just does not exist because it's a vertical asymptote. Okay, next, oscillating discontinuities. So when we're doing oscillating discontinuities, this is reserved for sine type graphs. Basically, the whole idea is like there's a couple of functions where like it just keeps cycling back and forth and saying, when do we hit 0? And you just never do because you're just cycling back and forth. There's a couple of specific sine graphs with it. I forgot to include one. I can't think of one off the top of my head. But basically what's happening is it just gets closer and closer and closer. It never actually hits 0, and it just oscillates between 1 and 0 because sine graphs like just constantly jump back and forth. So this is oscillating discontinuities. These don't happen very often. Oh, happy birthday, Jasmine. All right. So, takeaway. Basically, continuity is a setup for something called derivation and deriving. We'll talk about it later, but basically you do need to know how it's continuous. There are 3 ways that you can tell it's continuous. Number 1, f of x has to exist, and the way we check that again is we just make sure that there's no negative square roots and there's nowhere that I can become 1 over 0. Even if I had something like this, 1 over x, if my interval is something like from 1 to 5, then we don't need to worry. We can say it works on number 1. Because this interval does not have any place where it makes my denominator 0. So we're not breaking anywhere on the interval. So that's why we always talk about continuity over intervals or on a specific point. Okay. Secondly, in order for the limit to exist, you just check for piecewise. If there are no piecewises, then generally you're okay. That's a general rule of thumb. There are a few special cases, but I'll leave it to you to see if you can figure it out. I'm going to obviously throw 1 or 2 of them on future homeworks just to see if you're paying attention. But again, it's a general rule of thumb for the piecewise thing. And then finally, you want to make sure that 1 and 2 both have the same number. Your f of c is actually f of your limit. And then there are the different types of continuities. Make sure you know what they are, and at least they're able to identify them on graphs. Generally, they won't ask you what it is necessarily algebraically. They'll tell you, oh, this is a removable discontinuity, or this is something like that. So you just know in your mind, okay, I have one piece that pops out like that. Okay, last thing we're going to cover today, then we'll sing happy birthday to Jasmine, then I'll get to my meeting so that way I can figure out what we're doing next year. So we have intermediate value theorem. Intermediate value theorem is super simple, but it's something that students always screw up because it's so simple, but the application is like wonky. But basically, intermediate value theorem says this: if f is a continuous function on the closed interval a comma b, then y naught is some value between f of a and f of b, then f of c equals y naught exists for some c on the interval a b. Okay, Now let me explain the Morimoto definition. This is good for you to read back to, like it's important for you to understand mathematical jargon. So after I give you the Mori definition, it's good to go back and be like, okay, what's it actually saying? Mori definition says this: if the function is continuous and you can find an x value, then you can find an x value to get any y value between the endpoints y values. So basically, here's what we're saying. If I have something like this, 3 to 5, this is your interval. Then what we know is f of 3 equals -2, f of 5 equals 12. That means f of c exists for any number between -2 and 12. So if I wanted to say, hey, is there an f of c that gives me 10? The answer is yes. Is there an f of c where the answer is 0? The answer is yes. And the reason why that works is basically what you know is if I'm going to graph 1, 2, 3 here, and that's -2, and 4, 5, and this is 12, then in order to get from here to here, I obviously had to travel there. I can't just magically teleport from -2 all the way up to 12 without touching 0, without touching -1, without touching 11, 11.5, 7.666639527, or something like that. You have to hit every number between your endpoints y values in order to get there if the function is continuous. There's no way I can just magically jump from one to the other. That breaks the definition of continuity. That's what it's saying. So if I'm looking at this over here again, it's saying, okay, assuming that I have this function here, if I look at the y values on the endpoints, I can say that I can find any y value between them, right? I can find any y value between them with some x value between these intervals here. Whoa. Okay, I'm not sure why that decided to do that. Give me a second. What? On earth? Sorry, getting too hype up in here. Okay. Sorry about that. What? Okay. I don't know why my screencast is like constantly shutting off. And I have no idea why. It just doesn't want to cast to my desktop for some reason right now. I guess the only thing I can really say is my tablet really wants me to get to that meeting. It must be really important, I guess. So I apologize. We're gonna just call it there. Don't worry about IVT. I'm gonna talk about it a little bit more and how to use it. But in the meantime, let me just see reflector. In the meantime, that's the main thing with continuity. I'll be posting up your guys' homework with the continuity up right after my meeting. Assuming that everything goes smoothly. Today is just not a good day for me. Everything's just like shifting to today. I don't know why. It's great. It's wonderful. Any questions on continuity? Okay. With that being said, then, happy birthday to Jasmine. Everyone just in chat wish her happy birthday. We'll sing to her next time. Congratulations on being old. We appreciate you, Jasmine. I especially appreciate how you always are willing to say, no, we don't have any questions. Please move on with your life. Okay. If you guys have any questions, feel free to let me know. I'll post it up. Next meeting will be on Monday. We'll finish talking about intermediate value theorem as well as our next lesson. Hope you guys all have a great weekend. I know I've been slacking on the answer keys and some of the stuff. Sorry, it's just been a crazy few weeks. I'm going to a couple of trainings, as well as AP seminars this upcoming month, and they're just all hitting at once, and they're all just like, "Oh yeah, we forgot to send out when it's going. It's going on now." Stupid excuse. Sorry. But anyway, I'll see you guys later. Have a great day. Yeah, see you on Monday. Feel free to let me know if you guys have any questions. I know that we rushed this one. All right, see you guys.